Hello guys and girls, welcome to the computing workshop. I am the mad computer scientist and this is my workshop. This is the final session that we are going to have on the main introduction or first acquaintance with the Go programming language. Then I will probably do a follow-up video where we build some sort of web service to show the construction of services using the Go programming language, which is one of its main or key features is the simplicity for constructing services. So we will look at that, especially with the net HTTP and templating packages. But before we get to that, let's round up our initial acquaintance videos, getting acquainted with the language and the environment. And now we have arrived at one of those things that are often presented as a key point of the Go programming language, which is its parallelism, or basically the way it handles what is commonly known as multi-threading, and how simple it is to use these features of the language and of the compiler to allow for simple use of multi-threading and multi-processing and excellent scalability with garbage collection and good performance. So this is a key selling point, if you will, of the Go programming language that we're going to look at now, and one of its best features. It has its flaws. If you Google around, you will see there are some things that you can do that will cause problems. But all in all, this is much simpler than, say, the thread execution model of Java, for instance, which is with the thread pools and things like that. Here, everything is nice and easy to grasp, which is a good thing, because we want to get more developers working multi-threaded, and we want them to technically do it to provide scalable systems. This is even more important in today's microservices world, where you want to have small services which can then scale horizontally on demand. So let's look at the Go constructs. I will not talk anymore about multi-threading and parallelism, because that's a different question or topic altogether. So if you want to dive further into that, I suggest any good computer science literature on that subject in general. But the way Go handles this is by using two specific constructs in the programming language itself. One of them is the channel, which is used for inter-process communication. So it uses an IPC model of communicating between threads or parallel executions. Units of execution can communicate using channels, and these channels will pass values back and forth in a sort of safe way between concurrently running routines. This is the IPC pattern is not new in computer science. It's an old way of doing distributed systems, but Go has the construct of the channel. It also has the construct of the Go routine, which is the, if you will, if you come from a Java background or something like that, it's easier to think of the Go routine as this is the Go version of a thread. This is a separate unit of execution which can be scheduled by for execution at any given time, independent or asynchronously from the main thread. So the main thread contains your program, and then you can kick off parallel executions by calling functions as Go routines, and then you can use channels to handle if you need to synchronize back onto the main thread. If you don't need to synchronize, you just want to kick off computations, then just go ahead and kick off several Go routines, and these will eventually execute, and they will also execute in as much parallelism as possible, as determined by the compiler first and the operating system, of course, secondly. But it handles itself quite autonomously, like the async and await keywords in C# is a very good, very good analogy of this. But the Go way works with channels and Go routines. Okay, so I've written rather just now a small test program, and this time I've included all the code at once because it's not that much code. So we will just go over the code and look at how this works. First of all, I have created two functions which are just mock functions simulating some sort of computation. They are called compute and compute2, and here we are just taking a random number and we sleep for some random duration. This is actually milliseconds to make it a bit faster. So we sleep randomly. So the point is with this randomization is because as these will execute based on a lot of things happening in the background and in your operating system with regards to scheduling, then these could we want them to be a little bit apart so that we can then determine that it's actually executing asynchronously. So we have a randomization here in these mock functions. This is, by the way, a typical way in Go to create random execution times. I use this sometimes for mocking. Just get a rand dot, and this is math.rand. Just get a random, and then often it's sufficient to just sleep for this random duration of time to simulate something actually happening. So now going into our main function, which is where we are going to start to use channels and Go routines. So we first make a channel that we can use to communicate. So a channel is made, it's actually a type. So we can see here that channel is of type shan string. So shan is the keyword for a channel. And you use the make function just like you did with slices and with maps to create a new channel. And then you have to specify the type, and this type is the type of value that the channel will carry. So it can be, in this case, if you don't use one of these arrows in a direction here, you say that this is a bidirectional channel. It can both read, you can both read and write values with this channel. You can also create a channel which is read only or write only, if you want to do that. So this but this is a bidirectional channel, right? So then we kick off a new Go routine, and now we get to our second keyword, which is the Go keyword. So we say Go compute, and we pass in the channel, and this is normally how you pass in communication channels to functions that they can use to then communicate the result. Because remember, you want to maybe asynchronously await the result of this computation because you want to keep going here. You don't want to wait for a return. You want to kick off the function, then you want to do something entirely different, and then at a later time when you need the value, you want to read it from a communication channel, assuming that the function is done. Once again, a good way of a good similar functionality is found in the C# async and await keywords. Okay, so here we say go compute and we pass in the channel. So now we're calling this function and we're passing in our communication channel, which we have created here, which can be used to receive response from this function. Then we do now we can do two things here. We can await the value directly, which will block the main thread. This is a blocking call. Now we're saying we want to, here we can do other stuff in between here, but then we say that, okay, now we need this value. So now I'm going to wait. So we pause the main thread and we wait. So until there is a message on this channel, which is why the arrow goes in this direction. This is a bit of a tricky construct in Go until you actually learn to see this pattern as soon as you glance over it, in which direction communication is happening. But this is like you read it from left to right. You can see that you want to pull whatever is on the channel. You want to put it here in this this variable. So now we are taking out a value, and now we are actually blocking the main execution until there is a message for us on this channel. Then we can continue. But we could have done a lot of other things here in between while this was working, but now we're saying that we need this value to continue. So now we need some response from this channel before we continue, so we wait. Okay, now then we just print whatever is in this, what we received from the channel. Okay, or now we could also use the select construct, which is meant to say that we will wait for either of these possible communications, and then we want to continue and do something. Okay, so this is like a switch case statement but with channels. So we say here we make a second channel, and we call it channel 2, and then we call both functions that we wrote above, first compute, and then we call compute 2 on a separate execution, and we pass in the channel 2 channel. So now that we have two concurrently running executions, they're running in parallel here, or sort of in parallel. There's some discrepancy between them because of the call order here. But they each have a communication channel, which they can use to reach back to our main thread, the main program. And by doing this, now we can use the select statement. So now we can say this select block here, and we can use the cases to wait for either. So now we are saying that it's fine for us with whoever finishes first. We want to print that, and then we move on. Okay, so here we're saying that we are here waiting for a communication to happen, but we could take either off. So we could take either so here in this case we want to do something if the communication comes from the first channel, or we want to do something else if the communication comes from the second channel. We want to print message received from channel 2. So you can now synchronize your executions, and this is now there's no note that there is no memory management here or anything like this. This is also garbage collected like everything else. Very simple concept to grasp, but very, very powerful. This is a very, very powerful language construct for asynchronous programming and threading, or multi-programming, if you will. There's a lot of names in computer science literature for this. I will stick to parallel execution because that's really what it is. This is actually parallelism. If the operating system and environment allows it, of course, because in other cases it just becomes task switching, which you're executing several processes at once, but in linear time. But anyway, assuming that you have some way for this underlying system that you're running the program on to scale horizontally, like using more cores or spinning up new or like new CPUs or something like that, like in a virtual machine environment where you could create new vCPUs. This will be almost in parallel, almost because call order and functions is it's still dependent on the call order. It skews the parallelism, but not diving too deep into that discussion. Just note that you can do several things at once, and then you could use these constructs like either these blocking constructs or the select. The select is also blocking because here we are actually halting execution on the main thread until we receive a communication. Okay, so we can do other things here. Then we get to the select, and then we're saying that we need some sort of communication here to continue, either from the first or the second channel. Okay, so now, and that makes up our example code. So you can see it's fairly simple to work with multi-threading and with various types of parallelism in Go, because it has very nice constructs for this. And this is of course by design. It's not an accident. It's by design that it's very simple to work with. So given the areas where Go is designed to be primarily used. So if we look at this example code now, and we do something like go build, now go, and now if we run this example, we will see, okay, so if we straight up waiting in the first one to test variable, we compute 1 is done, and then we can see that the message received was from channel 1, and then we reached the end of the program. So we got a message eventually from channel 1. So that was the first one responding. If we run this a few times more, here we can see it directly happens so that this time we executed channel 2 was actually finished first. Or compute 2 was finished first. So we got a message from channel 2 before a message on channel 1, so we printed the second message, because we basically said here that we are waiting for either. And we want to do something different depending on the response we get. This is a very, very powerful thing, and you can do very powerful stuff with this. So I urge you to research this further. You will also see it used in the hopefully coming web service example, where this together with templating will be used. Hopefully I will create some sort of service that I can show you how web services are programmed in Go, which is one of the key usage areas of the programming language. So that's it for this part, and also for the getting acquainted with the Go programming language series as a whole. Now I urge you to investigate further, maybe read some book on the Go programming language that goes into more in depth about these things, and hopefully you had a good time, and I will see you again, maybe on the Go programming subject or a different subject, but eventually we will return to the Go programming subject, like I said, with some sort of web service. We'll see when I get around to that. So okay, thank you, and have a good time.